This is our last problem. It'll be the last problem that you do in the homework on homework 2. So honestly, I would, if you get to that problem, because that's a problem that students have have a difficult time with, so I would come back to this video and watch it again if you need to. We have 2.025 grams, so we've got to make that sure that's kilograms, right? Metal spheres have identical positive charges. So we've got these two spheres that have positive charges. They hang down from a light string that's 32 centimeters in length. So from here to here is 32 centimeters or 0.32 meters in length. It's attached to the ceiling. If the angle of the string from the vertical, so from the vertical to the string is 7 degrees, what is the magnitude of the charges? Well, we know that these two charges are repelling each other because they're positive, right? So these are those electrostatic forces, but what other forces are acting on them? Well, let's say we just focus on this one on the left, right? We have our positive charge, and we just said that it is being pushed to the left from that electrostatic force. Well, it also has gravity on it, right? So it has some weight, and we have this string attached to it that's applying a tension. Well, this tension force must be pulling to the right, and that has to be equal to the electrostatic force because it's not accelerating to the left or to the right. And the tension in the y direction must be equal to the weight of the object because it's not accelerating vertically, right? So we have three forces acting on it, and we know that Ty is equal to Fg and Tx is equal to Fe. Now, this angle here of 7 degrees is from the vertical, so in the force diagram, right, we are going to have to be from the vertical, so from the vertical, that is 7 degrees. Okay, well, think about our forces, right? Because we're going to be looking for, right, the magnitude of the charges. Well, both of these charges are the same. So in the equation F equals KQ1 Q2 all over R squared, if those charges are the same, we could really just say F equals KQ squared all over R squared. And as long as we know the R and the F, we can solve for the Q. Well, we know in the x direction, right, the sum of the forces in the x direction are 0, and that is our electrostatic force plus our Tx. And because the 7 degrees is here, this Tx is also like it's kind of up here. So because it's like it's up there, right, that's opposite of this angle that's in here, right? It's opposite, so that means we would use sine. So we could actually say that Fe plus T sine 7 degrees is equal to 0. And we could do the same thing in the y direction, right? The sum of the forces in the y direction is 0, and that is our force of gravity plus our Ty, and our Ty would be like T cosine 7 degrees, right? Because this is adjacent, right? This is adjacent to this angle in here, so it's going to be cosine. Okay, so it says now things become simpler. We can use this last equation to find the tension. Armed with the tension, we can find the electric force. Using the electric force, we can find the charge on the spheres. Because if we know the mass, right, if the mass is 0.25 grams, then that means it's 0.00025 kilograms, which means it has a weight or a force of gravity of 0.0025 newtons, right? So using that and the sum of the forces in the y that are equal to 0, we can say, well, the weight is down, so it's negative, and it's 0.0025 newtons. And then our tension y is up, and that is t cosine 7 degrees. And that means we can find that the actual tension in the string, which we don't really care, but we need it, is 0.00252 newtons. Right? So now I know that this is 0.00252 newtons. I can now go back and use my sum of the forces in the x equation. Right? So sum of the forces in the x is 0, and we know that Fe is equal to plus 0.00252 sine 7 degrees, right? That's what we said that Tx was T sine 7 degrees, and T is 0.00252. So this is Tx, right? So now we can solve for Fe, and we find that the force that's repelling those two charges is, let's see here, 3.07 times 10 to the negative 4th newtons. Right, so this force that's repelling and this force that's repelling is 3.07 times 10 to the negative 4th. Okay, well, if F equals K Q1 Q2 over R squared, which we said is K Q squared over R squared because the Q is the same, we can go through and we say, okay, well, here's our force because of those positive charges. So 3.07 times 10 to the negative 4th equals K, 9 times 10 to the 9th times Q squared all over, what's the distance? Well, if we focus on this triangle here, remember this is 7 degrees, and from here to here is 0.32 meters. If we just focus on our triangle, we can figure out what this distance is because it's opposite of the 7 degrees. So that means the sine of 7 degrees equals opposite. Let's just call this, I don't know, we'll just call it x, is opposite over hypotenuse. Right, so that means that x equals 0.32 sine of 7 degrees. Well, that's only from here to here. We also need the distance from here to here, right? We need r, which really means we need to double this. So 2 times 0.32 times the sine of 7 degrees, that is r. So we could put that in, right? 2 times 0.32 times the sine of 7 degrees. But remember, it's r squared, which means we have to square that value. When you plug that into your calculator correctly, right, so you do 3.07 times 10 to the negative 4th times 2 times 0.32 times sine 7 degrees, and then you divide all of that by the 9 times 10 to the 9th, you get q squared, but then you have to take the square root of it, right? And then you get q, and you finally come out with 5.18 times 10 to the negative 8th coulombs, which would be the same as 51.8 nanocoulombs. And so that is the end of it.